Thank you, Marlin. So I just shared my slides then. And yeah, I will talk about noise sensitivity and chaos in many variable systems, whatever that means, like systems consisting of many independent variables, like percolation process, spatial growth models, and similar kind of things. And I'm going to mention a little bit about recent work we've done, but also going to try to give like a more of a general overview of what these concepts mean and what we're trying to look for when we talk about these things. So yeah, let's get started. So I'm just going to start with a question and like an example here. Can be good to keep something in mind. So the question is like, suppose that we have some systems consisting of many independent variables. How does this system react when we perform a small perturbation, maybe resample a small proportion of those variables? And just to give something concrete, we can think of like the lattice in 2 dimensions assigned with weights on the edges, independent identically distributed weights. This weighted graph gives rise to a metric structure on the graph. It's going to be random, of course, because the edge weights are random. And we can look at the shortest distance between any 2 points. So this is like the model of fast passage percolation. And we can ask about this random metric, like how this random metric space, how is it affected if we just update a small proportion of the weights? And you can ask about different things of how it's affected, like is the distance between 2 typical points, does that change? Like given that you know what it was before, how will it have changed after the perturbation? Or maybe you're actually interested in something else, maybe like the landscape, like the geometry in this metric space. Like if you know where the shortest path between these 2 points were before, is it still going to be the shortest path afterwards, or will it has changed considerably? And while asking these questions, when looking into this, we will discover concept, or we'll discuss concepts like noise sensitivity and chaos, and I will explain what that means. And those are concepts that were introduced in different works, noise sensitivity by Benjamin Schramm in 1999, and chaos in, well, a decade later or so, in work of Surabh Chatterjee. So I'm going to start talking about noise sensitivity and explain a little bit what that means and its major application, which has been in the context of percolation. So Benjamin and Schramm, they introduced this concept in the context of Boolean functions. So suppose that we have some function we're interested in, taking entries that are zeros and ones, a string of zeros and ones, and outputs either 0 and 1, like in the context of percolation, maybe we have toss a coin to declare whether an edge should be open or closed, for example, independently among edges. But in the general context, we can think of a function, a Boolean function. And so we have some input, which we choose uniformly at random. Let's call that omega. And then we do a small perturbation of that input. Let's call it omega epsilon. So we obtain omega epsilon from our original configuration by independently resampling all the bits with probability epsilon. And then you were interested in, now, okay, so we had some configuration and a new configuration which is slightly perturbed. Obviously, locally, they are highly correlated. But could it be that when we look at some macroscopic properties here of the outcome of some function, depending on all those variables, that the correlation is very small? And that's what they refer to as being noise sensitive. And typically you have to look at some very large system, and as n goes to infinity, you declare your system to be noise sensitive if the correlation goes to 0. Okay. And as I said, this has been looked at in the beginning in the context of percolation. So in Bernoulli percolation, we start out with a lattice or any other graph, but a lattice, say the 2-dimensional lattice. and we declare the edges of the lattice independently open with probability P. And this kind of construction gives us a phase transition where we look at connected components, that points in the lattice that we could connected or reached from some other point, say the origin, by open edges, only traversing open edges. And this phase transition occurs at p equals a half when we have even coin flips. And that's because of planar duality. And it's a simulation that you can see precisely how it looks like at the critical point, p equals a half, where clusters that are connected, so points that can be reached only going across open edges, they are colored by different colors, and we can see like a large cluster that is colored yellow in the simulation, and that corresponds to like one connected component. And yeah, so by duality, we have that p equals a half is the critical point, and why is that? Well, that's because like just by symmetry, like if you have a square that you want to cross, a square which is not exactly a square, but like the horizontal axis is n plus 1 and the vertical one is n, and then having a crossing there of open edges, that occurs unless you have a vertical dual crossing blocking. And by symmetry, just by rotating the figure, well, they have that same probability at p equals a half. So this has to occur with probability a half, since both things cannot occur at the same time by planarity. So in percolation, we're looking at these long-range connections, the components that are connected at large distances. So if you want to ask about how this kind of system is affected when you do a small perturbation, that, okay, so had sampled all the edges being opened or closed. So we can do a small perturbation by resampling a small proportion of those points and declare them again either open or closed independently from before. So the question is then, okay, what should we mean by this system being sensitive? Well, here we have a good candidate, crossing a square that has probability roughly a half. So if in a configuration that happens, but then like when you do a small perturbation, how does that probability change? So given that you had a crossing before you do the perturbation, what is your conditional probability of having a crossing afterwards? Is that close to half? That means that the correlation is small. But if that's close to 1, when you have high correlation. And since we're interested really in long-range connections in this model, this is a suitable property to ask for, a suitable function to look for, like the indicator of this event. And this was the motivation by Benjamin and Schramm from the beginning, when they introduced the concept of noise sensitivity. And in the first seminal paper, they did prove that percolation crossings are noise sensitive. And they did that by developing certain methods, and central concepts like influences came into this. I'm not going to say much about their proof. Just going to say also that like this has been something that sparked a series of other really remarkable papers, like by Schramm and Steiff, Gerban, Petter and Schramm, and more recently by Tassion van de Wil, giving quantitative and sharper bounds on how noise sensitive this system is. And the latter two of these works give actually sharp bounds and tell you precisely how large a perturbation you need to have in order for the system to decorrelate. So having observed the crossing before the perturbation, after the perturbation, you will no longer have any information of whether there will be a crossing or not. Okay. So this is, and these results that are sharp rely on certain techniques relating to SLE and conformal invariance that are only known to hold for the triangular lattice, hypercalculation on triangular lattice. Okay, so I should maybe say also that this, as I showed this simulation here in the very first slide, that beyond the lattice setting, questions of noise sensitivity have also been looked at in continuum percolation, so in continuum models, where you can look for, again, you have a Poisson process of points, you can do small perturbation by deleting, like thinning your Poisson process slightly, and then boosting it up again by superpositioning a small density Poisson process. So you have just relocated some of the points, essentially. And again, in this kind of system, you will also have noise sensitivity. So you have two here figures where a large proportion of the points are the same in both of them. But not necessarily just because you knew that you had or could observe a crossing in the first, you're necessarily going to do that in the second picture as well because of this noise sensitivity. Okay. So noise sensitivity was introduced about 25 years ago and has been studied quite extensively in the context of percolation, but also in other contexts as well, like in random graphs and certain other contexts, but I'm not going to go into the full history at this point. Instead, I'm going to move on to the other topic of chaos and chaos in disordered systems and explore a little bit of work that was begun by Suraj Chatterjee. This goes back to a conjecture in the physics literature, conjecture from the 1980s. And this was conjecture in terms of spin glasses. So just to briefly describe what this conjecture was, well, pick a graph and assign to the edges of the graph IID Gaussian random variables. And these edge weights are referred to as the disorder of the system. And in this system, we're going to look at spin configuration. So you declare or you put spin up or spin down on all of the vertices of the graph and define the energy as the sum over all neighboring edges or neighboring vertices, their spin multiplied by this disorder variable. So if here, of course, the what is preferred here, what contributes to the energy is, well, this is the product of this the spin, so this is either plus or minus 1, but which is preferred depends on the sign of this disorder variable. So in many systems that we're used to, like in the Ising model, ferromagnetic Ising models, then you have phase transition depending on a temperature parameter. So at low temperature, the system tends to divide into an order phase. So you see like plus spins and minus spins separating. Whereas at high temperatures, you see the spins mixed up because you're above a certain barrier where it doesn't cost so much to have disaligning spins. So what's typical with this disordered models, the spin glass models, is that there is no such phase transition. Really, rather, the disordered phase is what you will see at all temperatures. And we refer to the spin configuration that minimizes the energy as the ground state of that. And a conjecture from the 1980s was that this ground state, this object minimizing the energy, the spin configuration, is actually sensitive with respect to small perturbations of the disorder. So by changing just a few or like a small proportion of these disorder variables, you would typically see a large change in your spin configuration being the ground state. So this is where the conjecture comes in. And the first work in this direction is a paper by Aldous, as far as I know. And what Aldous was looking at was not at spin glasses themselves, but rather at matchings on the complete graph, or complete bipartite graph. So you equip the complete bipartite graphs with IID exponential random variables, and a matching is a subset of edges that include every vertex once. And what Aldous was studying was the minimum weight matching. So among all matchings, the one that has the least total weight. And this is a set of models, like these kind of combinatorial optimization problems, were a set of models that physicists thought, well, they resemble quite a bit properties of these spin glass models. So like it's kind of interesting to study them for this reason. And in Aldous, in his work, he settled a conjecture describing or telling you what the expected weight is. It converges to pi square over 6 of this minimum weight matching. And moreover, could show that any matching that differs from the minimum weight matching in at least delta n edges has to have a significantly higher weight, has to have at least pi square over 6 plus epsilon. And this was, in fact, rather negative information with respect to the conjecture of spin glasses, that this kind of suggests that you do not have this chaotic behavior that physicists had conjectured. Well, maybe that does not say so much about the conjecture itself, but actually rather that these combinatorial optimizations problems are perhaps not that close to the spin glass behavior that you expect them to have. So maybe they're just toy models in that sense. Okay. But later work of Saurabh Chatterjee, well, this was first published as preprints in like 2009, but came out later in the form of a book. So Saurabh Chatterjee was the first one to like try to approach this in models more like the spin glass models, and actually was the first to obtain positive result in this direction. So to describe this context that Saurabh Chatterjee was working in, so let's look at the lattice just described. So he did this for different models. Let's just give one example here, just to give you a flavor of what the results is. So let's look at the square lattice, and now assign IID weights to the vertices of the lattice. And let's look at directed path of length n starting at the origin. And a directed path is a path that goes either to the right or upwards, but is not allowed to go back. And we're going to define the travel time as the sum of the weights picked up along this path. So this is a last passage percolation problem. You can also think of it as like a polymer model. And so we're going to denote by pi the path that really attains the maximum. Now we want to maximize the weight picked up along a path, and t its travel time. So what Chatterjee proved was that if we have Gaussian weights on the vertices, and the perturbation is dynamical in the sense that the weights evolve according to independent Ornstein-Uhlenbeck processes, then it could show that chaotic behavior, which in this context meant that, well, if you look at the polymer, like the ground state, the optimal path picking up the maximum weight in the original configuration, and the optimal path at a later time point t, when you have run your dynamics for time t, well, those paths are length n, and if they've changed drastically, well, then they must look quite dissimilar, like a small proportion of the vertices that you visited in the first one must be also visited in the second one, but most of them will be completely different. So chaos, as Chatterjee defined it, was that the overlap, like the vertices visited by both these paths, is a smaller order than the length. So the length n, so if their overlap is little o n, then that is chaos in Chatterjee's framework. So, and he could prove that chaos is actually equivalent to the travel time itself having a sublinear variance growth. And this is what Chatterjee referred to as superconcentration. And thus established in this set of models that he was looking at that superconcentration is equivalent to a chaotic behavior of this model. And he could also prove that this model is superconcentrated and therefore could deduce that it also has to be chaotic. Okay, so so this was the first evidence of chaos in these systems, where you look at rather the object that is maximizing or minimizing, optimizing in some sense, your energy or travel time or whatever it is you're looking at, depending on what you want to call it, depending on what your model is supposed to model.
Is the 2 dimensions important?
No, 2 dimensions is not important. In this context, it's not important. I think that in Chatterjee's original work, I think this equivalence was in any dimension. The variance bound that he could prove is sublinear was only in 2 dimensions, but that was later extended to other dimensions. So no, it's not important.
Okay.
Of course, precisely what's the right order of things here will depend a lot about finer things about the model. So there the dimension does come in. Okay, so Chatterjee's work was the first in this direction, and he did this in terms of Gaussian disordered systems. So Gaussian part here, like the variables were Gaussian, and the perturbation was in terms of Olshan-Uhlenbeck process was important here because that was the framework that he was working in. But what he was looking at was this kind of polymer model or a last passage percolation model, but also like random matrices with Gaussian entries, as well as certain spin glass models, like on the Sherrington-Kirkpatrick model of spin glasses on the complete graph. So he did give several instances of evidence for chaos in this context, in the Gaussian context. And this has been later elaborated upon. Bordunov, Shubakovsky later looked at Wigner matrices with more general weight distributions or distribution on the entries of the matrices, and could show there also chaos of the eigenvectors corresponding to the largest eigenvalues of those matrices. Ganguly and Hammond looked further into the spatial growth context. So they looked at a Brownian last passage percolation model, where they proved chaos of the geodesics, the distance maximizing path. Together with Dave and Sfragara, I looked at this myself, in both in the context of first passage percolation, we want to minimize the travel time, and last passage percolation, we want to maximize the travel time. And also recently, Chatterjee again gave evidence of chaos in the Edwards-Anderson model of spin glasses, which is more like a lattice model of spin glasses, maybe being the most interesting to physicists in this context. And there's also simulation of how this could look, like if you have last passage percolation in the plane, looking for the optimal path between the lower left corner and the upper right corner, directed path. The path can go either rightwards or upwards. And you see the original path being in blue, I think, at time 0. And then if you resample a small proportion of the vertex weights, then you see that the red is your new geodesic optimal path. On the left, you have a small perturbation. You see that, okay, so for some stretches, they look completely different, but at several stretches here, they still look pretty much the same. They overlap well, so you still have a large overlap. Whereas on the right, you see that even when the paths come close, they really don't seem to care very much where the other is going, so they really do not share many vertices in common. So you do see this chaotic behavior having appeared. And let me also emphasize that some of these works gave really precise results, like already this result of Bordenave, Lugosi-Sivakovsky, and also this work of Ganguly and Hammond. And I want to mention this, since I did mention this, that we had sharp results for noise sensitivity in the context of percolation on triangular lattice. That's also known in some of these models. The transition where we go from stability to chaos, and let me highlight this work of Ganguly and Hammond for the Brownian last passage percolation model, where they could show that like the threshold is like n to the minus 1/3 in terms of the side length of n being the side length of the square you're looking at. That's where you go from having a large overlap to having a small overlap of these distance maximizing paths. Okay, so that's a little bit about what is noise sensitivity, what is chaos, and what has been done, like some of the main papers that have been written on this topic. I want to continue and talk a little bit about the relation between the two and see what's the difference really. Can we put that into more words, or is that just because you're looking at different models? Do these things, are they really the same thing, just that you have different terminology in different contexts? So I would like to emphasize that there really are two different things. And I want to, so for this discussion, I'm just going to focus on the last passage percolation setting. So let's just fix some notation, and so we just to have something concrete in mind when we continue. So again, look at the square lattice, assign IID weights to the vertices, and then we resample weights independently, and we do that after a uniformly distributed time. So I can think of this again as a dynamical process. After time t, each vertex has been resampled with probability t. And let omega t, let that be the weight configuration at time t, and let t index t be the travel time. Again, if we go in the context of last passage percolation between the lower left corner to the upper right corner of an n by n square. So tt will be the travel time at time t, and pi t will be this path, the optimizing path. And it doesn't really matter if we talk about last passage percolation or first passage percolation or something related. I'm just going to have something in my mind now that I continue talking about this. So what would it mean to have noise sensitivity? Well, if we go back to how it was defined by Benjamin and Schramm, you had like a function of many variables, and you perturb a small proportion of the variables, and you look at the correlation. So sensitivity would correspond to correlation of T naught and T sub T being small. So correlation going to 0 as n going to infinity. Chaos, on the other hand, so noise sensitivity says something about the travel time, but chaos says something about like the path, which is the optimal path at that given time. So for the chaos, we would instead look at the overlap between the geodesic at time 0 and at time t. And well, the length of these paths are order n. So them having a small overlap would be their overlap being little O of n. So that's what chaos would mean in this context. So one thing, noise sensitivity talks about the travel time, whereas chaos talks about the paths that are optimal for this particular landscape at this particular time t. So there are two different concepts, and they're not equivalent, not necessarily equivalent. So if we would like to understand a little bit how one would go about to prove something about this, like prove noise sensitivity or prove chaos, like where you would start would be like looking at the covariance. So the covariance at time 0 and time t, we can, if we introduce this function qt, so it's the function of like measuring the covariance at time 0 between time 0 and time t, then we could express the covariance as qt minus q1. So at time 1, everything has been resampled. So t0 and t1, they're completely independent. Because at time 1, everything was resampled from what you had from the beginning. Okay, but then this is a difference of a function in one variable. You can write that as an integral if you want, like the integral over the derivative of this function. And if we plot this function, maybe it looks something like this. Clearly, as time increases, you have introduced a larger perturbation, so naturally would expect that the correlation would decrease with time, and that's also not so hard to prove, so that is certainly the case. And if what you start out with at time t equals 0 is where you have the variance. So if you want to prove noise sensitivity, then well, you want the correlation to be small. So you want the covariance at some time epsilon, say, you want all this path or this curve already to have been dropped very far down, close to the axis. That would correspond in this picture to noise sensitivity as we defined it. Okay, so it would have to have a very sharp decay in the beginning to reach or close to the axis very soon. Okay, so we started out here with writing the covariance as this integral. So what if, can we make sense of what we're integrating over, this derivative of q? And here's where we come back to the influences. So I said briefly that influences were part of this work of Benjamin and Schramm when they started out looking at noise sensitivity some 25 years ago. So what is the influence? Well, the influence is essentially measuring how much does a certain variable or coordinate matter for your function. Okay, so what does that mean? Well, suppose that we have now our function t evaluated at time t. So this d is going to be the difference of your function t if we force coordinate v to take the value x. And what we get if we would do the same, but then we average over all possible values at that point. So we're looking at how much could your function change if we over the span of all possible values. So that a coordinate could take. And so this is essentially like looking at our function and the conditional expectation when we use the average over one edge or one vertex. Okay. And what's the influence? Well, the influence is roughly how much does this, how much is this difference? How much does this vary on average? But we're going to talk about the dynamical influence, or like the influence measured at two different points in time at the same time. So I'm going to define the influence of a vertex V at time t as looking at this difference for t naught and this difference for t at time t on average. Okay, so perhaps this is a little bit strange, or perhaps it's very natural, but the reason that I do want to refer to this as influence is that when you look at specific case, for example, for Boolean functions, it does boil down to something we're familiar with. So if I look at the influence of a vertex at t equals 0, so I'm really looking at the square difference on average, then it turns out during the calculation that this is roughly is a quarter times the probability that if I change coordinate v to 1, what's the probability that this is different from what I will get if I put coordinate v to be 0. And this is really like what this probability is really how you usually would define influences in terms of Boolean functions. If you instead look at the influence of the vertex at time 1, well, then we're looking at t0 and t1, which are essentially independent, except for the behavior here in this particular vertex v, because that's what we have put here to be x in both cases. So we're integrating over that together. And doing this computation, you see that this boils down to also something which is similar. You get similar expression, just that you get this probability squared. So this is for Boolean functions. It boils down to something that we're familiar with. The first thing is what we would refer to as the influence. And the second is that influence squared in that case instead. Okay. And why is this relevant? Well, it's because with this notion of influence, we can write a formula for the covariance. The covariance is precisely what you get when you integrate over the sum over all the influences at different times. That is to say that, like looking at this graph again, where we plot the covariance as a function of t, then the sum of the influences is recovered as the derivative of this curve. That's what it was like. The curve was q, and the sum of the influence is the derivative of q, with a minus sign, so that it's, of course, decreasing. Okay. And one thing that we can observe here is that, well, if we want noise sensitivity, well, what we wanted was that, like at a very small point in time here, we wanted the covariance to be already very small. Like here, up here, we had the variance, and we want the covariance T naught, T epsilon to be very much smaller, of a smaller order than the variance in order to have correlation close to 0. And when does this happen? Well, if that to happen, well, this derivative, the inclination of the curve, cannot be very large before, if you're going backwards from 1 towards 0, the inclination, this derivative, cannot be very large until before you get to epsilon, because if it was very large, well, it will jump up, and then you will have a large increase of your curve, and then the covariance is not going to be small in comparison to the variance. So we see that noise sensitivity essentially requires, or that you have that the influence, the sum of the influences at time epsilon being of a smaller order than what the variance is, right? So if one could show that, one would get noise sensitivity. But this covariance formula is also relevant for obtaining chaos, because what Chatterjee observed and what has been observed in other contexts later is that the sum of the influences, well, you can actually relate the influence of a vertex to the probability that that vertex is actually used by your minimizing object or maximizing object, the geodesic in this case, if we're talking about last passive percolation. So if you have a vertex which is far away from the geodesic, your optimal path, well, changing that, the weight at that point is not going to have a large effect because the path is not going to care, it's far away already. But if you change the weight of a vertex on the geodesic, well, then it will actually change the travel time. So you can relate the influences to the probabilities of being on the geodesic. And if you have the influences at time t, like this dynamical notion of influences, well, that corresponds to the vertex being influential both at time 0 and at time t. So it has to be part of the geodesic at time 0 and also part of the geodesic at time t. And summing over all vertices, this gives you the expectation, the expected overlap between the geodesic at time 0 and at time t. Okay, so as such, chaos is derived as a consequence of anomalous fluctuations, because what you have here is that, well, now we plotted here the sum of the influences instead, and which is then essentially the same as the expected overlap. But if you integrate over the sum of the influences, what you get is the variance. So the area under the curve here is the variance. And up here you had n, that's just the length of a typical path of a geodesic. So if this is going to be small, or you have going to have chaos, then the sum of the influences has to be little o n. But if the variance is little o n, then this comes for free, right? Because like if this red curve does not decrease very quickly, then the area under the curve is going to be order n instead. So there you see that also from this kind of covariance formula, chaos also comes naturally out. Okay. So drawing these two curves next to each other, we see that we have a relation here between noise sensitivity and chaos. So noise sensitivity meant that the first curve here on the left, it goes very rapidly down to 0. Chaos meant that the second curve, it goes very rapidly down to 0. And we saw that chaos we would obtain that if we had the sum of influences being little o of n, whereas for noise sensitivity would require something stronger. We would really require that the sum of the influences being of a smaller order than the variance, and the variance is typically in this context growing sublinearly. So proving noise sensitivity would be a larger challenge typically in this context. That's at least what this indicates. And that's maybe why I also have mentioned several results here proving chaos in this kind of settings, but there are much fewer examples of noise sensitivity in this kind of context of spatial growth models or related models. So I just have a couple of slides to conclude what I've been saying. So we've seen a little bit about the relation between noise sensitivity and chaos. If you look at spatial growth models like chaos, we have seen several papers deriving chaos in this context, chaos of the GD6. We have not seen much evidence for noise sensitivity. And as I said, that's because that we see that that's kind of looks like it's a harder question. It's like you require to say something about the sum of the influence in relation to the variance of them. But there is some evidence, and this is maybe the first paper in this direction. There was a paper I wrote together with De la Riva. And so we looked at the simplified model of first passage percolation, because in first passage percolation, things were hard. We could not resolve the question. We could not prove that the travel time between 2 points is noise sensitive. So we tried to simplify it first by looking at the square instead already, but that was still too hard. Like looking at a square, having the crossing from the left to the right, the minimum weight crossing. So what we ended up doing was so let's look at specific weight configuration. So let's assume weights take value A or B with equal probability independently, and look at crossings that are paths crossing from the left to the right, but with a very narrow transversal fluctuation. So let's assume that we only focus on paths that have transversal fluctuation at most n to some small power. And this power happened to be 1/22. 1/22 worked for us. Okay, let's denote the travel time over this set of paths as tau. Tau is a random variable. It has some distribution. This distribution has a median. So we could, in order to get to a context where we're working in a setting with Boolean functions, we can look at the event that Tn exceeds its median. And that's what we showed. We showed that this sequence of functions is noise sensitive, giving like some evidence of noise sensitivity in the context of fast passage percolation and spatial growth, but simplifying the model before we could say something about it. Okay, so noise sensitivity in this context is still much of an open problem, and we still seem to struggle to understand that. So the last thing I wanted to say was also about noise sensitivity and chaos. Like in this discussion we just had, it seemed like, well, noise sensitivity would imply chaos. We saw that to prove noise sensitivity in the context of spatial growth, we would need to prove something like the sum of the influences being of a smaller order than variance. Whereas for chaos, it was enough to prove the sum of the influences being little o of n. So I don't want to leave you with the impression that this is necessarily the case always. In fact, it's not true in certain settings, and it's a little bit more subtle than that. So this happened to be what we now discovered in the context of spatial growth models. But as I will tell you about in the next talk, is that if we look at mean field stable matching, so also some kind of combinatorial optimization problem, we do not see the same behavior. In fact, noise sensitivity does not imply chaos in that context, but I will leave that to Mia to tell you more about that in the next talk. So thank you.